So in the first part of this discussion, we talked about what earthquakes are and what causes them, movement of plate tectonics, or tectonic plates, I should actually say. And then we looked at what, excuse me, the aftermath of these earthquakes. So like the kinds of damage they cause, and then the accessory things that come along with earthquakes, uh, tsunamis, landslides, the fires that break out, and things like that. In this discussion, we're going to talk uh, pretty much just strictly scientifically about characteristics of earthquake waves, which we really call seismic waves. And then a little bit on how you assess the energy that comes out of an earthquake, because some are short and relatively quiet and they're over soon. Others are really violent and the ground shakes for, up to a minute, which isn't a very long time. But when the ground is shaking up and down as much as 3 or 4 feet, that minute would be absolutely terrifying. So let's get into this. We have been attempting to analyze earthquakes for a really long time. But really, it's only in a modern sense that we really understand what's happening. So seismology is the scientific study of earthquakes. That's the name of the particular science. The instruments that record earthquake waves, if you've seen in a movie where there's like a little needle and a piece of paper on a drum, the needle starts to quiver a tiny bit and then it starts to shake dramatically. We're looking at a seismograph there. Those are the instruments that record earthquake waves. Actually, that's not exactly the case. What you're looking at is a different type of instrument, but it's connected to the seismograph. So here's one of the earliest devices that was designed to sort of measure earthquakes. This comes from either China or Japan. I don't remember. But each of those dragons would have like a steel ball in its mouth. And when an earthquake would come by, the waves do move in a direction. So maybe they come from the east, like the wind can. So the idea was it would make the marble fall out of the dragon and the frog would catch it. So you would look towards the direction where the marble came out, and that would tell you where the earthquake came from. And they tried to figure stuff out based on that, but this never really got us anywhere. Here we can see by demonstration, these are really super simple examples of what a seismograph could look like. The machine on the left, you can see it's fixed firmly to the ground. So the instrument will shake, but the pendulum there, because it's on a spring, the arm, it's articulated and it's on a spring. So the heavy weight will actually appear to stay relatively still. It draws those lines by the ground going up and down, and it moves the entire rotating drum with it. And then on the one on the right side, earthquakes can shake side to side as well. So having that heavy weight suspended by a string, the idea is the arm and the drum below it moves back and forth and traces it there. In reality, they're much more sophisticated than that. So these waves can detect earthquakes that we cannot feel. The vast majority of earthquakes, remember, more than 99% of them are pretty much undetectable to us, but they're there. And seismograms can take seismograph data and interpret it for us or amplify it for us. So this is what I was saying earlier. The little machine that you see actually trace the zigzags back and forth like in a room where there's a bunch of people sitting in there. That's a seismogram. It's connected to a seismograph, which is deep underground, that's recording those waves. So here's an example of one right there. That is the seismogram, and it's connected via wires and whatever else to a seismograph that's buried deep below the ground. And this looks kind of messy to us, but we can break down earthquake waves. They arrive in stages. So you can see the first peak on the left, and then the next peak in the middle, and then there's the really energetic peak, the one kind of right in the middle, but the furthest to the right here on there. So it's kind of like sound and light. You can see somebody like maybe shoot a gun from really far away. You see the flash of the gun before you ever hear the sound of the bullet, because it takes the light waves get to you right away, but the sound waves travel way slower, so there's a gap there. And we see that with different kinds of seismic waves too. And of course, the waves radiate in all directions. They don't just travel straight up, straight down, or straight outward, all directions. But some waves can only travel through certain material. So light, for example, we can see the sun. Light waves can go through outer space. Sound cannot. You can't hear anything in outer space. But sound can travel through, oh, this is a bad example, but like a telephone, because the sound doesn't actually travel through it. But you can't see anybody through a telephone. I guess today we can FaceTime, so maybe that was a terrible example. But anyways, a type of wave called a surface wave is a type of seismic wave that can only move through the top layers of Earth's crust. That's it. So these waves don't go through our planet, but body waves do. They can travel through any part of the geosphere. Now, it's true that I don't think we have any, but let's say we have a seismic detector in South Dakota. We could detect an earthquake happening in China with it, but we would only be able to record the body waves because China's basically on the opposite side of the planet. The surface waves would never get here. They lose their energy traveling through the crust before they ever get here. But the body waves, because they can travel right through our planet, they can. There are two types of surface waves. The first type are called shear waves, and they move through the crust in either an up and down or a side-to-side fashion. We say they move in right angles. And these can go through any part of the crust. So these waves can travel along sometimes even more than 100 miles below the surface, depending on how thick the crust is. But surface waves, so this is weird. There are two types of surface waves, and one of them is called a surface wave. It doesn't make any sense. These ones can only move up and down. They have the greatest energy, but they only go through the very top layers of Earth's crust. So if, like, theoretically you were in a mine shaft or something a mile below the surface and an earthquake happened, you might not feel the surface waves. I don't know what the depth is that they can go down, but that's just a hypothetical example. And then as far as body waves, we have just one type. They're called P waves or compression waves. Now these are different. They compress and expand the rock, deforming it by changing its density. This is kind of hard to explain, but we'll talk about it in class. Now a P wave can travel through solid, liquid, or gases. Obviously earthquakes don't transfer into Earth's atmosphere, but studying earthquakes has told us about the interior of our planet. And a lot of you, I think, already know this. Our outer core is liquid, and we know it is because of earthquakes. These body waves travel through the Earth, and the liquid layer of our outer core stops or allows them to keep going, but stops other types of waves. So the key here is P waves have the highest velocity. Then the shear waves have the next highest velocity, and surface waves have the slowest overall velocity. But their energy is backwards. P waves have the least energy, S waves have more, and surface waves by far have the highest energy out of all of them. So the slowest moving wave can cause the most damage, right? A seismogram will show you all three of the types of waves. So that really simplified one that I showed you earlier shows first the P wave, then the shear wave, then the surface wave. If we focus on the very top here, you can see what they're doing with that spring is the person is pushing it forward, and that compresses part of the spring and then expands other parts of it. So that creates what we call a compression wave, and that travels back and forth. That's what P waves do. Whereas surface waves, you can think of it, you could do this with a spring also, but like a rope or a spring or something, shake it either back and forth or up and down. That is what surface waves do. That's how they move. And then if we compare them, if we suppose that this grid that we have on the left represents Earth's crust, we can say P waves, notice how they affect the entire crust all the way from top to bottom. If we look at the S wave, the shear wave, notice how it affects the entire crust top to bottom. But if you look at the surface wave, Notice how it only influences the very top layers of the crust. That's important because that's the key difference between the two. So here's just the aftermath of some earthquakes, and nobody would build a road that looks like that, obviously. It'd be fun to ride a bike or a skateboard down, but not a car. So it's been deformed by surface waves. You can see it's gone up and down. Here we can see a road that's been shooken, I don't know how to say that, side to side, which surface waves can also do. So anyways, with some labels, here's all the different waves. The amplitude, which is how tall, for lack of a better term, the waves are, that tells you how much energy they have. So notice that the P wave, it has the least amplitude, has the least energy, but it gets there first. We have time at the bottom here. We can see exactly 30 minutes later, the S wave arrives, and then 10 minutes after the S wave, or in other words, 40 minutes after the P wave, the surface waves hit, and they have way more energy. Well, that just shows us the same thing. Now, the good part about that is we can use it to precisely determine where earthquakes come from. I don't know exactly how long we've been able to do this, but it's fairly recent technology, like it was developed in the 1900s, and it works in a really cool way. So the farther the P waves and the S waves travel from the epicenter, the more spread out they become because of their difference in velocity. So think about this with me. We have a person that's walking and a person that's on a bike, right? And they start off from the exact same location at the exact same time. Go. Okay, let's say they travel for 5 seconds. How big of a gap is going to be between them? Well, not very big. It's only been 5 seconds. But what about after 5 minutes? Well, now all of a sudden the gap between them, we would imagine, is gigantic. So if we came across a biker and a walker, and we had no idea how long they'd been traveling, we could just look at the gap between them, and we could say, okay, let's say the gap between them is 500 feet. All right, you just run it backwards. How much faster is the bike than the person walking? And you divide that for time and you figure out the distance, and you could figure out where they both started from. And that's what we do with earthquakes. By measuring the gap between these P waves and S waves, which constantly is growing, we can determine the distance of the epicenter. So these are what we call a travel time graph. And I'm going to do this so you can see my mouse. So this is the velocity of the P wave. So this is minutes, so this is our time, and this is our distance. So notice how if we go to, this is sitting right at 13 minutes. In 13 minutes, a P wave can go 10,000 kilometers, which is really far. In that exact same amount of time, so if we stay on this flat x-axis here, our time is remaining the same. In 13 minutes, an S wave can only go 4,200 kilometers. So that's the gap between them, right? Now, the way we actually use these is you would wait until you detect a P wave, and then you measure the gap between them. So let's pick a spot that's right. Let's pick this spot right here, because this will be easy to read. Here's the P wave. Okay, start the timer. Tick tock, tick tock, tick tock. It appears that exactly 3 minutes goes by. So this got here at 4, and this gets here at 7. Exactly 3 minutes goes by, and the S wave now appears. Okay, so we consult the graph. We wouldn't use this graph until we have the time between the P and the S wave. It's been 3 minutes. This is our 3-minute gap. So we line those up and we go straight down, and we know that the epicenter is 2,000 kilometers away. Great. But here's the problem. What direction is it? That we don't know. It's 2,000 kilometers away, but is it to the north, to the south, to the west? We have no idea. All we can do is draw a 2,000 kilometer wide radius around us. And we don't know, that doesn't narrow it down very well. So now what the heck do we do? Well, that's the next step here. As long as you have 3 different locations all of those circles that you draw will converge on one and only one location, and that's where our epicenter is. This is how GPS satellites work. So like for your phone, it can figure out where you are to the nearest inch, right? But it will only work if there's at least 3, and they usually shoot for 4 satellites above your head. So for your phone, in order for the GPS system in that to work, like I have an Apple iPhone, the map system that Apple uses, they've had to launch more than a dozen satellites into outer space. So think about how crazy that is. A phone company had to build satellites and consult with a space company like NASA or whatever, I don't know how they did it, and get these satellites into orbit, orbiting our planet, just so that you can figure out how to get to a restaurant in a town you've never been in before. World's crazy. So here's an example of this, right? So let's say you were on the Yucatan Peninsula and we had our example from before. All you know is that the earthquake is 900 kilometers away. So you draw a 900 kilometer wide circle around you. Let's say another station is in the middle of the ocean, so it's kind of a bad place for it. But it knows that the earthquake happened farther away than that, in this case twice as far away. We don't know if it's here or here, right? So that's where you bring in the third. As long as these calculations are done correctly, they will only converge on one point. So that's where our earthquake happened. And here's just another example of the same sort of thing. There are patterns to earthquakes. Remember, earthquakes happen where there are faults, where plate tectonics or tectonic plates meet. But those faults are all different. Some are pushing into each other, others are pulling away from each other, and others are sliding past one another. The plates that are pushing into each other, if you just think about it, those are the ones that create far more earthquakes than plates that are pulling apart from each other. Because where's the tension in things that are pulling apart, right? Colliding plates create these huge amounts of stress and strain and elastic buildup and way more earthquakes. 90% of all the earthquakes that happen every single year happen on the border of specifically the Pacific plate. So that plate, it just happens to be that pretty much it's almost everywhere around its boundary, it's crashing into other plates. So this is the Pacific plate right here, and these arrows show what its movement is. So here it's converging, there it's converging, coming together, coming together. Now here it's pulling apart, but if we just pick on coastlines instead, we can see that, yep, those are coming together, that's crashing into that one. Well, it's not exactly centered the same way. I can move it though, so that it is. But here is a map of earthquake epicenters. So look at the shape here of this right there, and notice how perfectly it matches with the Pacific plate. It's pretty much uncanny, right? You get this weird shape here, that loop, this arc, another loop. Well, look what we have. Arc shape, a loop, another arc, and another loop over there. Now, each of these red dots is an individual earthquake. So the fact that there are so many over here just shows that it's a big density, it's a big cluster of earthquakes happening. Notice how this line over here there's not nearly as many earthquakes there. Why so many here and not here? What do you think the difference between this plate boundary and this one is? Well, that one right there, or at the bottom of Africa, is a diverging one where they're pulling apart. Yes, earthquakes happen, but there isn't nearly as much tension. So these earthquakes are far less common, and they're also far less energetic because there's just so much less stress built up. Everywhere we have them coming together, like here in India where the Himalayas are, here in South America, and then all along the Pacific, that's where we have, look, these big densities of these things. Notice how dense the dots are together there. And the other location was India, which is right over here. Look at how many dots there are. Fits perfectly. This is just sort of a side note, but this is a map of every volcano on our planet too. 90% of all volcanoes are around the Pacific Rim too. we'll get into why that is later. Historically, we use two methods to describe earthquakes. Intensity isn't really super scientific. It's just a measure of how much shaking occurs in one region. So you measure this in centimeters, millimeters, meters, feet, inches, whatever you want to pick. So you're actually describing how far up and down the ground was shaking. That's intensity. But it's true that, let's say, two earthquakes happen in two different places in the world, and both of them move the ground up and down by 3 feet. That doesn't mean that both earthquakes were the exact same, or that they both released the exact same amount of energy. So intensity is just a term we use to assess like building damage, describe the characteristics of the earthquake. Magnitude is an actual calculation. So we can actually figure out exactly how much energy was released to cause one of these earthquakes. And we can compare it to other things because there's many different ways of assessing energy. The Richter scale really isn't used anymore. I don't know if the news is still using the Richter scale or not. I don't think they are, but it could be. The way the Richter scale worked is you have your waves and they go up and down, the amplitude. You pick the amplitude of the largest wave and you derive the energy from that. And it ranges from 1 to 10, but it's logarithmic, which means a 2 is 10 times stronger than a 1, but a 3 is not 20 times stronger than a 1, it's 100 times stronger than a 1, because you have to multiply by 10 at every step. So how many times more energetic is a magnitude 6 earthquake than a magnitude 2? We just add 4 zeros to it. A 3 is 10, a 4 is 100, a 5 is 1,000, a 6 is 10,000 times more energetic than a 2. That's a big difference. The one that seismologists use today is called moment magnitude. And this can calculate the total amount of energy released during the entire earthquake event. Because a Richter scale just takes a snapshot of like one instant of the earthquake. Moment magnitude can calculate the entire energy of the whole earthquake. And it's calculated by this formula. You don't have a bullet for this on your notes, but write it down because you need to know this. You take how big the fault is, you multiply it by how far the fault shifted, and then you have to take into account the rigidity of the rock, because in some places, Earth's crust is not nearly as tough, so it would be easier to move, and in other places, it's made of much more solid types of rock that are more dense or whatever. So there we have it. Oh, no, not quite the end. I guess I just want to show you this. Worldwide, there are around 1.2 or 1.3 million earthquakes every year. But look, 90% of them, well, not quite 90% of them, but if we go up to a magnitude 3, that's where like 90% of them occur. We don't really notice them. But there are a few every year that are really strong. Most of them are, happen in remote places. But, magnitude 3 would be the equivalent of the world's largest nuclear test, apparently, or the Mount St. Helens eruption. So there we go. And here's some more numbers, approximately like how many of these earthquakes occur all the time, every year.